Hi everyone, and welcome back to another edition of the Data Idols and Data Science Festival Summer School. I'm Jess, the Community Director at the Data Science Festival, and I'll be your host for this event. So, this session is going to be part 2 of a 3-part mini-series on Intro to Machine Learning. It's going to be around classification. There are 2 more other sessions, regression and clustering, so if you have time to watch those other sessions, please do so. If you're watching this on playback, and watch them because they're great as a 3 mini series. In a second in the chat, you'll see there'll be a link to our Slack channel. Please join that, chat to other attendees, ask questions, and we're also there if you need any help. If you're watching this on playback, as I said before, congratulations, you've made it through probably a lot of sessions. So keep going, you're almost at the end. So just wanted to say a massive thank you to all of our partners. It's been an incredible experience getting to know each and every one of these companies. They've spent a lot of time putting all this content together, rehearsing, and also presenting these. So we are very grateful for every single one of our partners who's made this summer school a reality. One of those partners is Compass Lexecon, who've been integral to making this 3-part mini-series. So this session is going to be on classification, and Rashid and Enrico are going to be taking us through that from Compass Lexecon. So hope you enjoy the session and see you at the next event.
Hello, everyone. Welcome to the second of Introduction to Machine Learning sessions in the summer school. Today we'll be talking about classification alongside my colleague Enrico. So just a quick overview of our plan for the next 45 minutes to an hour or so. So I'll give you a brief intro. Who are we? Who is the company that we work for? We'll then give you a little bit of an overview into what is classification, how does that differ from some other machine learning tasks that we might want to do. We'll then go into a little bit of a deep dive about one particular type of classification algorithm. We'll talk about some of the how we actually train the model, how do we interpret it, how do we know how well we're doing, and towards the end we'll then talk about a different type of classification algorithm that's actually something completely different, but still achieves the same goal. Hopefully this will then provide you with a nice set of baseline tools, baseline knowledge, such that you can then go away and kind of study these topics more on your own, or be able to really interpret documentation and so on in a way that you can kind of go off and then run away with it. So just quickly about us, I lead the data science team in Compass Lexecon. I started off my career as an economist. Some might say I then saw the light and spun off into the world of data science. I spent a bit of time at Deliveroo, and I've now kind of combined my two loves of economics and data science in Compass Lexecon, where we apply data science techniques to problems that we face in our organization. Enrico has a similar background to mine. Also an economist who dove in headfirst into the wonderful world of data science. He does a lot of work on neural networks, NLP, and similar to myself, likes geeking out about these things at any given opportunity. Before we jump in, just a quick overview of Compass Lexecon, our company. So we are an economic consultancy firm. That sounds a bit vague. So what we do in practice is we help clients, we help law firms, we provide advice to government organizations around issues related to economic questions, or more specifically microeconomic questions. So for example, competition policy, will a merger be good for consumers? Will a merger be bad for consumers? Is a certain practice that a company is doing bad? Is it good? What are potential damages of such actions, and so on. So we essentially take economic theory, we do rigorous empirical analysis, and as of the last year and a half, when we started the data science team, we now also apply kind of modern data science techniques to provide support to our clients across the various areas in which we work. While you might not have heard of us, we've worked on over half of the biggest merger cases in Europe. including, for example, Google Fitbit, FCA Peugeot, various mergers in, say, banking and agriculture and so on. So we really kind of span across a very broad range of topics, very broad range of industries. And part of the reason I'm saying all this is because we are hiring. So if any of this takes your interest, please do jump onto our website and have a look at that. Cool. So that's done for the intro. Now into the good stuff. Let's talk a little bit about classification. So classification, like I said, is one type of machine learning category of problem. And generally, this is one that comes up in a lot of areas. So whether you're kind of in business, whether you're in policy, whether you're in science, we're often, typically interested in understanding the relationship between, some kind of input and then some kind of output. I mean, the same is true of kind of regression problems. So some examples are here in the classification context are, in e-commerce, if you're a company trying to selling various products, you maybe want to understand what option is my customer most likely to buy. In a banking industry, you might be wondering, I have all of these clients, which one of them is most likely to repay their loan, which one of them might not want to repay the loan. In image recognition, we might have, that's also a classification problem. So, is the picture a particular type of food? So is it a hot dog? Is it not a hot dog? That's a reference to Silicon Valley, if anyone has watched that. Marketing is very common. In NLP, it's very common. So, very often we essentially want to take the data that we have about some particular thing and then make a prediction about whether something will happen or something else will happen. These are all different types of classification problems. So in some cases, we want to identify one amongst many options. In some cases, we want to only be able to predict one or another option. In some cases, the different options are ordered. So for example, in the case of education, we want to understand what is the highest level of education someone might achieve based on, for example, their income, where they live, and so on. There's different kind of levels. So even though classification sounds like a pretty simple task, there's lots of different nuances. It actually encompasses a very wide range of different use cases and different problems. To make it a little bit more precise, in both regression and classification, so if you have attended the previous talk by my colleagues on regression, we have kind of a similar setup. So we have some observations, and just to explain a little bit this notation, will normally represent the data that we observe about someone, the features by X, and the outcome, so the thing that we're trying to predict, by Y. So we have observations 1 through N. If we want to be kind of a little bit more formalistic, our data will normally show up like something like this, which is a data set where we have an observation, a row for every single observational unit that we see. So this might be, for example, a single person or a single town or whatever it is that we're studying. We'll observe some outcome Y. So for example, that could be whether the person buys product A or product B. And then we observe a bunch of features about them. So each column is a separate feature. It might be something like their income or whether they bought something previously or so on. So the key difference between regression and classification is that whereas in regression, Y is continuous, what we mean by that is that it can take sort of any value on the real number line. In classification, the problem is different because Y can only take one of some discrete set of values. So it can either be 1 or 0, did someone do something or did they not do it? It could be one of, for example, 10 choices. But the key thing is that, it can't be in between any of the two choices. So even though in principle, we have some X, we have some Y, and we want to draw a relationship, the problem setup is quite different from one of kind of classical regression because we have to make a lot of different choices about how we model certain things. But despite that, we're kind of interested in the same set of questions. So, is there a relationship at all between the input X and the output Y? How strong is the relationship? We might want to know which of the inputs, so which of the features are most important in driving our prediction or in the relationship. We might want to understand how strong is how accurately can we actually measure this relationship? We might also want to know how accurately can we actually do a good prediction, which is a slightly different problem. I've been talking a little bit in general terms, so now we can dive into a more concrete example that will sort of be following through for the rest of the presentation. I mentioned at the start that one example, and this is taken from the Introduction to Statistical Learning textbook, which I kind of very strongly recommend everyone to look at if they're learning about machine learning, is the default data set. So what we have here on the scatter plot is simulated data about a hypothetical bank that has a bunch of clients. So each observation here is a single client. Those clients have a certain income level and a certain account balance. So what an account balance means is how much money do I owe to the bank? So this dot over here says that this person has, a salary of $10,000 and they owe $2,000 in debt. So, and then what we want to predict, or rather what we want to understand better, is can we predict whether a certain person will default on their loan? So this person owes £2,000, maybe from their overdraft, maybe they've taken out a loan. And these red dots indicate those people that in this data set have defaulted. So it means that they've said, sorry, we can't pay the loan. And then, then something happens. I mean, the bank loses money and then there's some process. So our task here will be to try and understand this relationship. So what actually determines, can we systematically understand whether something will, whether someone is more likely to default on their loan or not? And immediately we can kind of see, well, if we draw this vertical line here, it seems that there's quite a few more red dots here than blue dots, and here it's mostly blue dots. So we can already kind of say, okay, maybe we can split this data set somehow. Maybe we can use some techniques to do that. If we look only at the account balance dimension, we can kind of see that the groups are a little bit clearer. So we see that the people who default on their loans tend to owe a lot more money. So whereas the people who don't default on their loans kind of have a debt of around, 1,000 to 500 to 1,000. Those that do are kind of closer in the 1,500 to 2,000 range. So immediately we can look at this and say, well, maybe if we try to understand the relationship between account balance and default, we can start doing a few of these prediction tasks that I spoke about. So let's look only at account balance for now. This is again just a slightly different way of showing the data, where we have account balance on the x-axis, and then whether someone defaulted on the y-axis. So we've essentially taken away the income dimension for now. So what we say, first the thing we have to do is sort of encode the data. So a typical way of doing it that is saying, if something happened, call it 1. If something didn't happen, call it 0. And then we just plot it here. So we see that there are a bunch of, let me turn on the laser pointer. So we can see that over here, we have kind of every single dot again as a single client. And of those that defaulted, we see an account balance sort of between 1,000 plus to 2,000. And then these are the ones that didn't default. So let's try to use this and try to kind of estimate this relationship that I just talked about. One thing we might want to do is say, hey, I did the linear regression class. Why don't we run a linear model through the data? And that's perfectly valid. It's a perfectly kind of mathematically and statistically sound thing to do. And if we do that in this case, we get something like the following. So this is the linear regression line of best fit. I won't talk too much about how we actually estimate the model, but what it does give us is essentially for any given level of account balance, it can tell us what is the predicted probability that the person will default. So what it says is, if we say take someone with 2,000 account balance, we look up against this line and we say, okay, maybe they've got about a 0.2, a 0.25%, 0.25% probability of defaulting. This is fine, but I guess first question is, how do we then turn that into an actual prediction? We have a probability. One common thing that we do is simply say, okay, well, if the probability is greater than half, we say that default. If it's less than half, we say that they don't. But looking at this graph immediately, we see that, we have some issues. So the first thing that kind of worries anyone is that you actually have a lot of predictions that are less than 0. And in fact, had we had more data or the data is different, there's nothing in the model to stop it from making a prediction greater than 1. So that's already quite bad. And then the second problem is that, we haven't yet defined what fit is, but we can kind of see that the line doesn't really fit the data very well. It's kind of quite closely stuck down here. In fact, we would probably predict that no one would default because the line doesn't cross the 50% point. And this is where logistic regression comes in. So logistic regression is sort of the first antidote when we realize that the linear model is no good. What if instead of drawing the straight line, we can actually draw a line that looks a little bit more like this? So one which stays closer to 0 for low levels of the account balance, and one that can go kind of a bit closer to a prediction of 1 for high values of the account balance. And this is a very common approach when dealing with this sort of data. And this is what we're going to focus on for the first substantive part of the discussion. So what we're going to talk about is, well, how do we actually estimate such a curve? How do we figure out the values that we need to be able to draw it? How do we interpret the results? And how do we know how well we're doing, most critically? And so what the main kind of thing to understand with the logistic regression is the logistic function. So this is the reason kind of it's called logistic regression, and it's this kind of not quite scary looking expression, but getting there. So what does this say? This says that we predict some probability of an outcome happening based on some input x. And the way that we do that is by passing in 3 things. So we pass in the data x, so the value of the account balance. We pass in some parameters, beta. And from here, we can then pass it into these exponential functions, and from there get a sort of a function. So what this is saying is that if we want to, for example, predict the probability that someone defaults for an account balance of like 1,950, all we do is we simply plug in this 1,950 into this equation, and we get a value of 0.4. So kind of just reading it off this line. What's quite good about this function is that essentially it doesn't ever go below 0 and it never goes above 1. So already it becomes quite a useful, we know that it can probably be a bit more useful to model probabilities, because probabilities always have to be between 0 and 1. Again, there's one missing step though. We got to go from probabilities to a prediction. And so one common thing that we might do is essentially say, okay, well, let's call it class 0 if the probability is less than 0.5, and class 1 if it's greater than 0.5. And so this is quite nice because it gives us a cutoff value above which for account balance above which we would predict that the person will default on their loan. So this is all good, but here comes the sort of most critical part. It's, okay, we've plugged into this equation with these betas, but what we actually want to do is get some values for these betas. So what we want to do is to estimate the model or train the model, and in doing so, we will get values for these betas. So let's go back to our logistic function and try to understand a little bit better exactly, we see betas up here, we see x's and betas down here as well. We can rearrange it a little bit to make it a bit simpler. So if we see here, we kind of, take logs of the exponents and so on, and we get an expression which represents the same information. We see that this linear relationship, beta 0 plus beta 1x, is equal to this particular expression, which is called the log odds ratio. So whereas previously we would, in linear regression, we say if you increase x by 1, it increases y by beta. Here, if we increase x by 1, it increases the left-hand side by, the probability by this expression. And so, we want to kind of get the estimates for these values such that we can learn what the change in this ratio will be. Got a floating animation point, apologies for that. So how do we do that in practice? Well, as with regression, we first need to define a cost function. What a cost function does is it tells us how well a model is doing, basically. So we have some betas, beta 0, beta 1, and now we need to know, is the model actually good for that level of betas? And so what we're doing with the cost functions is just quantifying how far away we are from the line, from the real data. And the cost function normally will, we won't normally see this when we're actually doing the training, but I think it's very useful to understand, is that, if for different values of beta and for different values of beta 1, we have some cost. So cost is here on the z-axis. So it might be the case that for some low value of beta 1 and low value of beta 0, the cost is very high. What that means is that the model is not fitting our data very well. The goal of the training exercise, the goal of the estimation is to say, can we find this point here in this entire parameter space? So can we find the value of beta 0 and beta 1 where the cost is as low as possible, so our model fits the data as well as possible? And you can, in principle, define any cost function you want. Now, whether that gives you a good model or not is a different question. So there's quite well-established cost functions for different problems. And in logistic regression, the kind of most common approach is to kind of go back to some of the statistical foundations of this approach, which I won't talk about, but it's to use something called the likelihood function as our cost function. So you might sometimes, when reading about logistic regression, hear terms such as maximum likelihood estimation, which is all basically the same thing as what I'm about to talk about now. So kind of going back, just a quick reminder of what our logistic function looks like. So for some given values of parameters beta 0 and beta 1, our prediction for the observation I is yi hat. So hat, we normally say this is the predicted value. And we predict that by putting in the data x for some given values of the parameters. The log likelihood, and bear with me with this slightly complicated mathematical expression, is given by this expression. So what this says is, this is a mathematical expression to show essentially, to represent that same curve that I just showed on the previous slide. But it's actually very satisfying. So if we kind of think about this a little bit more closely, we see yi here, and then log yi hat, 1 minus yi, and log 1 minus yi hat. We take this for every single observation and just sum them up together. So no fancy multiplications, no nothing. That's already kind of making us feel a little bit more at ease. The second kind of nice thing about this cost function is that our yi, because we're looking at a single classification outcome. So something either happened or it didn't. This cost function will kind of simplify quite a lot once we plug in the data. So if yi is actually 0, so if the person didn't default, this entire left-hand side of the equation disappears because yi is 0 and anything times 0 is 0. On the kind of right hand of this expression, we see that the opposite would be true. So if the data says that this individual I did default, then this term will disappear. Okay, so we've defined this log likelihood function. Let's go into understand it a little bit better by focusing on the case when y equals 1. So when y equals 1, like we said, this right part of the equation will disappear, and we only have this left-hand side of the equation. How do we make it as small as possible? Well, if you remember that the log function looks like this picture here on the right, we know that the log function will take a value of 0 whenever whatever is inside of it is 1. So, and making something 0 is a good way of making it as small as possible. So what we're going to do is assign the cost a value of 0 whenever y hat equals y. And that's quite satisfying. So what's going to happen is that if we find beta parameters that mean y hat is very close to y, we'll end up with a very small value. And so the cost will be very low. The same will be true for the other class. Now, you don't actually need to worry about this too much once you're doing it in practice, because any tool in Python or R or so on will essentially do all of this for you. But I've often found it's very useful to understand these things, especially as we kind of go into slightly more complex models. So I've spoken about kind of a logistic regression with two classes, with the 0 and 1. Now, obviously, that's a little bit simplistic. In reality, we would probably want to do, I showed you the data set which had many columns. And in fact, this model extends very easily to that. So, previously we'd only looked at beta 0 and beta 1, but there's no reason that in this logistic regression specification, you can't add kind of up to k variables, so as many as you really want. And in fact, the maximum likelihood estimation, so the cost minimization thing that I showed you on the previous slide, applies just as easily as that. And again, you don't really need to work through the maths yourself. Whatever software you're using will do that for you. We might also want to consider examples that I discussed previously where you have more than two outputs. So, for example, if I'm considering whether a customer will buy one of many options. There are ways to extend logistic regression to that. So, for example, you might want to run one versus all classifiers that are sometimes called. So predict whether something happens versus everything else, and then do that for every single class. In practice, we wouldn't necessarily choose to do that. There are other methods, for example, linear discriminant analysis or classification trees that tend to be a little bit better. Well, both in general, but also in the case where you have multiple responses. Good, so we've estimated our model. We know kind of how the maximum likelihood will give us some parameter estimates. Now we need to kind of decide, well, is our model actually good? So how do we understand how well we're doing? And so in the example that I showed you above, so the curve that I showed you, we have a training error rate of only 2.75%. So, fitting our data, only 2.75% of the individuals in that data set are misclassified. So does that mean we have a good model? Well, no, and for several reasons. The first is that, training error will always be lower than test error. So whether our model can predict the data that it's seen isn't actually a very good model. What we care about is how well does our model perform on something that it hasn't seen yet. And something a little bit more subtle is that, if we remember the chart that I showed at the beginning of the presentation, not that many people actually default on their loans. So very few of the observations are actually read. So, in this case, only 3.3%. so this kind of brings up a quite fundamental concept that I think maybe people don't think about as often as they should, which is, what if we just have an absolutely dumb classifier that only always predicts that someone won't default? Well, in that case, our error rate will only be 3.3%. And so you might conclude that, hey, my naive classifier that doesn't actually do anything is quite good. So, that gives us a pretty good lower bound. But that also shows that maybe we should kind of think a little bit more about the decisions that our classifiers are making. And so let's look at kind of exactly the types of mistakes that our classifier might make. And one kind of very convenient way to do that is using this idea of what's called a confusion matrix, not least because it probably confuses people, as I'll show you on the next slide. But if we think about it, a classifier will predict, in this case, one of two things. It'll either predict that something happened or that it didn't happen. And we can look at that, how it compares to what the true value. So if we predict that something happened, that the person defaulted, and they actually did, that's what we call the true positive. If we predict that they didn't do something and that actually is the case that they didn't do something, that's a true negative. And then there's these two types of mistakes. So one could be a false positive, so that you think that the person did something when they didn't, or false negative, which is that our model said that they didn't do something when in fact they did. And this is quite a nice way of looking at it, because we can immediately say, actually, let's just try put the things in red, make them as small as possible, put the things in blue, make them as big as possible. Now, obviously, that sounds a little bit trivial, but that's essentially what we're doing whenever we're building a classification algorithm and when we're tuning it. Now, if you think about it, you can maybe divide true positive by false positive. You can do various calculations on it, because ultimately, it's convenient to have a single number that we're looking at, or a few single numbers. And there are a lot of different calculations you can make from basically one simple little matrix. They all have confusing names. They all have different ways of calculating them from the same four numbers. I won't go through all of these because that'll take up, a couple of hours and not be super exciting. But it's useful to know a couple of these, because there are some that you will see quite often whenever working on these things. So this is the actual output from the classifier that I showed you earlier. This is done in R. And the output for a certain confusion matrix package gives you the actual confusion matrix. So sometimes here it's called reference, whereas I called it true value earlier. And we have a value for the prediction. So we see here that 100 cases, 100 observations were predicted to be true, where in reality they were true. Equally, 9,600 were predicted to be 0, when in reality they were also 0. And then we have 233 mistakes of this kind, of ones of a false negative, and 42 mistakes of a false positive. There's a couple of kind of little statistics here that will be mentioned that come up quite often whenever discussing classifiers. So one is the true positive rate. Sometimes people call it recall, and that says how many true positives are there. So how many true positives did we predict, divided by the total number of positives. So in this case, and that's called the sensitivity. Often in like medical statistics and in science, they call it sensitivity as well. So in this case, we have 333 actual positives. 100 of them were predicted to be true, and so that gives us about 30%. And so if you think about it, we said earlier, our model has a 2.7% only makes 2.7% error rate. But actually, then once we start digging into it, we're kind of surprised to see, well, actually, yeah, in total, we're not making that many mistakes, but we're not actually that good at catching the positive ones. On the other hand, if we look at, for example, a different metric called specificity, that's kind of what's sometimes called the true negative rate, and that's the equivalent. So it's as the positive one. So that says how many true negatives divided by how many actual negatives. And this is, 90, it's pretty much 100%, so 99.6%. And that kind of makes sense. So we've predicted a lot of them to be negative, to be 0. And we've only kind of misclassified 42 of them, which sounds good. But then again, if we remember what the data looked like, there was actually not, it was mostly negative data. So, a simple dumb classifier would get that right, 100% of the time. Finally, the last statistic that I think is quite useful to think about is something called the precision, or sometimes the positive predicted value. And that's to say, of all the entries that we predict to be positive, how many are actually positive? And again, it's just dividing a couple of these values. So we're saying, of the true positives, of the predicted positives, 100 were actually positive and 42 were a mistake. So that gives us a rate of about 70%. These are all useful numbers because they give us kind of good way of really understanding what are the types of mistakes that our classifier are making. And that's very important because different use cases essentially have different requirements for what types of mistakes are acceptable. If we're thinking about, for example, medical screening, we might want something that might overdiagnose people as positive, for example, of a certain tumor being cancerous or of a certain X-ray being problematic, because we know that what that's going to happen afterwards is that a doctor will look at it and verify it, whether that is correctly the case. The mistake the other way around of saying, hey, everything's fine, but it not being fine is much higher. So we might want to, for example, choose the parameters of our model such that we make more of one mistake than the other. And just kind of going a little bit more into this idea of model assessment and types of mistakes that we're making, we can extend it a little bit further. If you recall previously, what we said is that a prediction will be positive if we predict that the probability of something happening is greater than 0.5. However, that's, while statistically that sort of makes sense, if we're kind of working in a machine learning context, we might want to be able to flex that a little bit. What if we choose a different threshold? So can we do better actually if we change the level at which we're happy to determine whether something is positive, like I just kind of said for the medical example? And we can do that. So we can actually just run the classifier. So we can train the classifier once and then make predictions based on different thresholds and get different confusion matrices out of them. So here we pick a very low threshold of 0.1. And so we're essentially predicting quite a lot of cases to be positive. So here now we've predicted, 700, almost 800 cases which were actually negative. If we increase that threshold, we see that this value decreases. So we go from predicting about 770 to 100 to 200. We can do that further. So this is the example that I showed previously. So kind of by changing the threshold, we get different confusion matrices, we get different positive rates, true negative rates, and so on. And we can actually plot that. So we can run the model, we can run our predictions for a bunch of different values and essentially just show this on a curve. So we can plot the false positive rate against the true positive rate and then see, okay, for different levels of my cutoff, what is my true positive and what is my true negative, and then understand, how much of a trade-off are we making. So going from here to here, are we happy to tune our model a little bit? We might increase our false positive rate, but we're increasing our true positive rate by quite a lot. So that kind of seems like a sensible trade-off to make. We might tune it a bit further, increase our false positive rate even more, but also increase our true positive rate to, for example, 0.75. And again, maybe that's a trade-off we want to make. If we keep doing that further and further and further, we actually end up with a bit of a bad model. So, if we say only classify something as positive if the probability is 100%, well, then we have a pretty useless model, which is kind of makes a lot of mistakes, even though it classifies all the positives as positive. And this is called the receiver operating characteristic. I think that has something to do with engineering, why it's actually called that. But very broadly, any model where this curve is as close as possible to this top left, so sort of hugs that top end of the curve, is a good one. And so you'll very often see this kind of statistic called AUC, area under the curve, which tells us, how big is this area? If this line is diagonal, that tells us that, our model is not going to do very well a lot of the time, regardless of what threshold we choose. One that kind of is up in the top left, so has a high true positive rate and a very low false positive rate, is a good model. So that's all I wanted to say about kind of model assessment and classification in the context of logistic regression. At this point, I will throw in a Monty Python reference and hand over to Enrico, who's going to talk about K nearest neighbors classification, a slightly different approach, and kind of the associated pitfalls and things to look out for. So at this point, I hand to Enrico.
All right, so as Rashid said, now let's talk about something that is slightly different compared to logistic regression. Let's talk about K nearest neighbors, and which is KNN for short. KNN is a type of classification algorithms, but actually can be used for both classification and regression. In this presentation, we are particularly going to focus on the classification characteristic of the KNN algorithm. I'm going to start by talking a little bit about the algorithms, the intuition itself, to give you some characteristics of the algorithms, then talk about a little bit about the implementation, and finally about the pros and cons of the KNN algorithms. So let's start with the intuition of the KNN algorithms. So the idea is that you classify data points by looking at the neighbors of a specific data point. So let's consider an example. Let's consider the figure on the right-hand side of the screen. In this figure, you can see we have some training data, which is the data in the little gray clouds. You can see you have data with different labels. So you have data with the light blue labels, red labels, and then black labels on the right. And then you have a brown dot, a big round dot in the middle, and that's our test point, our data point that we want to classify. And for this specific data points, we don't know the label. The label for this data point is what we want to predict using the KNN algorithms. So as I said, we are gonna try to predict the label for this brown dot by looking at the neighbors. And so the idea is that by looking at what's around this data point, we're gonna look at the labels that the data points around the brown dots have, and then the labels that appears most frequently within the neighbors is a label that we're going to use and assign to the brown dots. So that's the general idea. So, and the intuition, I guess it's quite simple. But what I wanted to stress is pretty much two main things around for this algorithm. So one is that you have K nearest neighbors. So the data scientist had to select how many neighbors he wants to look at every time he wants to predict a label for a specific point. And then the decision rule is based on a majority voting, what is called majority voting. Majority voting basically means that you're going to assign the label to a point based on the label of the training data around it that appear most frequently. And that's majority voting. As you can see, I mean, this type of algorithms is an approach to classification is kind of different compared to the logistic regression approach that Rashid presented earlier. Particularly in this method, this is a method is called like non-parametric model. Indeed, while before for logistic regression, you notice that we had like a function was a linear function that was helping us to map the input and to the target, to the labels. Right now, we don't have any type of functions. So the model is completely free for any type of assumption, and it's basically classifying dots completely with complete freedom. And so this is why it's very different. And then the second thing is that while before, we saw that we have a sort of an application or implementation of the model that was based with two steps. A first step where it was focused on training time using training data, and then a second step where you were predicting labels, doing inference. Here instead, the KNN method is a little bit different because there is not really a training time and an inference time. Everything happens at the same time. So the training data and the test data are used at the same time. And actually you're using the training data immediately to predict the label for a specific instance. And this is why it's called instance-based learning. So this is pretty much the characteristic and the overall intuition around the model. What I wanted to discuss now is probably to go a little bit further into the details, into the inner workings of the KNN algorithm. So as I said before, the starting point is always training data, and this is true for pretty much every machine learning problem. So you have some training examples, X, and you have their specific labels that we're going to call it Y. And again, as we saw before, the training data are the little dots in the gray clouds around, and the labels in the specific color. And again, you have three main labels. So you have black dots, red dots, and light blue dots. And then you have a test example, Z, which is again, these brown dots that we want to classify. So now how the algorithms just select the neighbors and apply the label and apply the label to the brown dots. So the way it does that is again kind of intuitive. So for the brown dots, it starts calculating the distance between the brown dots and any other dots that are present in the training data set. So it calculates the distance d from z to any other x in the training example. After that, it select the k closest examples and look at the labels. And finally, it predicts the output class for the example Z. And again, this is based on majority voting, as I said before. So it's going to apply the class, it's going to assign the class that appears most frequently within the neighbors. Just to give it, to make it a little bit more real, if we look at the brown dots here, and let's say that we want to look at 8 neighbors around the brown dots. Probably the closest 8 neighbors are around these 2 red dots here. Then you have 4 light blue dots and 1 black dots here. So these are the 8 neighbors. Then what you're going to look at is you're going to try to apply majority voting. And so the class that appears most frequently is the light blue class. So you're going to apply the light blue class to as our prediction of the label for the brown dots. So this is basically really simply how it works. But there are 2 main things here that I mentioned. One is the distance that we're going to discuss a little bit later. And the second one is k, is the value of k. In this case, in the example I just given, I said, let's consider the k equal 8, so the 8 nearest neighbors. But actually, as you can think, I mean, this type of algorithm is relies kind of heavily on the value of k, right? So particularly if you can think that if k is too small, the model has a sort of high variance when it's going to make a prediction. Let's say that k is pretty much equal to 1, then it means that the algorithm is going to look at just the closest point to each of the test points that you have. And so it's going to do that for any test point that you have. And it's very likely that the type of prediction that it's going to make are going to be very different for each of the points, depending on the closest neighbor, even if these points are the test points are kind of close to each other. Instead, the opposite is that if the k is too large, the model assigns probably everything to the most probable class, so to the class that appears the most in the data set. And so when you're applying this method, what you need to do, you need to sort of try and test the different type of values of k. You can see in the figure in the slide there are different type of, this is an example of k nearest neighbors applied to some data, and you can see a different subplot for a different value of k. So going from left to right, so you can see when k is equal to 1, you can see the decision boundary, which is the black line, which is very jagged. And again, you can see that there is sort of high variance kind of prediction. And then when you move towards the right, instead you can see the decision line, instead it's kind of boom, smooth. So the variance is definitely lower, and this is probably a value of k that is kind of high for this problem. So what you need to do is that there is, when you apply the KNN method, there is not really like a specific rule of thumb. What you really need to do is to really try different values of k and try to find the one that works well for your data and for your problem. But in the way in which you do that is by taking your training data. And remember that the training data is basically your starting point. Is that all the data points for which you have their location in the space, and also you have information about their labels. And what you're going to do, you're going to set aside a fraction of this training data, which is called your validation set. And then you're going to use your training data and your validation set to try and test the different values of k. Basically, your validation set, each point in the validation set becomes sort of your a test point that you want to test whether the model is able to predict the label correctly or not. And what you're going to do, again, you're going to try different value using the training and validation set, and then try to pick the value of k that works best, pretty much for your data and for your model. So the value of k is pretty much the main job. It's up to the data scientists to pretty much set up that value. But that's not the only thing the data scientists should focus, should be worried about, should take care of. I mean, there are some practical issues around the use of the KNN algorithms. So I said before, and I said also a couple of times, that the decision is made on majority voting. And you can think that, well, a majority voting may work well most of the times, but sometimes it may happen that you have sort of tie breaks, right? Because what could happen is that you look at the neighbors, and then you might have just red dots and blue dots around your test point, but the number of blue dots is equal to the number of red dots. So what are you going to do in that case? Are you going to decide? Are you going to predict the label for your test point? Well, so one trick most of the times is to pretty much use an odd number of neighbors, so that you never have like tie breaks. I mean, this works, but generally it works for binary classification problems. So whether you have to classify like text in spam, not spam, or whether you have to classify blue or red dots. But in case you have like multi-label, multi-classification problem, in that case, it's not going to work anymore. And so usually in order to solve tie breaks, what you're going to do is you can either flip a coin to determine the class a data point belongs to, or you can assign the class that appears with pretty much with greater probability. Or finally, what you can do is to sort of conduct a one nearest neighbor search around your test point and use the label of the nearest neighbor in order to as your prediction. Again, as before, for the value of k, there is not really like a way that is better than the other. You really have to have a look at your data, your problem. You have to try it out and check the performance of this. And the second practical issue is around scale. So as I've seen before in the different charts, you have each point or each of your training data and each of your test points as a sort of a specific location in space. And also in order to find the different neighbors, you have to calculate distances. So what you have to make sure before applying the KNN, you have to make sure that each dimension is a sort of a same or a similar scale. Otherwise, the calculation of the distance to find the neighbors might not be correct. Another issues might be around missing values. So missing values are not allowed in KNN. So you always have to spend a little bit of time to fill the missing data set, or at least do something about it before applying KNN. And then the final point, which is an important one, is around the distance metric. So usually the calculation of the distance between data points is based on the Euclidean distance, which is usually, this is the default choice for KNN, and it works for continuous data. But that's not the only distance metric that you might use. So there are many different ones. So some they might be more robust or more sensitive to some things, or some that might work well with continuous data, but not work well with categorical data. So for instance, for categorical data, you might want to use Hamming distance compared to like Euclidean distance. And again, as I said before, for the value of K, here you have to try to test and the different distance metric and choose the one that work best for your type of work and the data as well. So finally, what I would like to talk about and to summarize a little bit is the pros and cons of this method. So as I said at the beginning, this is a method, is a non-parametric method, and one of the big pros is that it doesn't make any type of assumption about the data or any type of function to map the input to the target values, which is a very big thing. And the second pro is that it's intuitive. So I hope you find it intuitive as well, and also it's relatively easy to implement. However, it has some cons, right? So it might be sensitive to outliers and also to mislabeled data. So particularly if you have mislabeled data in your training data set, that could be a big issue when you're looking at your neighbors, and especially if you look at just a small number of neighbors around your test point. Also, it requires you to handle missing values before you can apply, and that could be an issue. It could be also a lot of work. And finally, a very important point is that it can be very computationally expensive, both in terms of memory, because you have to store like all your training examples, but also in terms of time, because it requires you to calculate distances between your test point and any other training and any other points in the training data set. And depending on how large your training data set, this can become a very big exercise, very computationally expensive. So this is everything I wanted to say about KNN. Hope you enjoyed.